Alright, here we're looking at problem number 3 from Thermo homework, worksheet number 4. We're looking at how much energy in kilojoules will it take to heat 1,550 grams of ice from negative 70 Celsius to room temperature of 25. We see that it's ice. Let's see if we can write here. So we recognize that it's H2O, or water. So if we sketch out our curve to find out what we need to calculate, remember, since it's water, the melting point and freezing point are 0, and this boiling point is 100. Okay, this would be different for different substances. We see water a lot, so that's what it is. So we're starting at negative 70, which is obviously below 0, so we're down here somewhere, starting at negative 70 degrees Celsius. We're heating it to 25 degrees Celsius, which is in between 0 and 100. So we're somewhere in a liquid phase. Okay, we're above the freezing point or melting point, but below the boiling point. So we're going to have these three sections. We've got section 1, section 2, and section 3. Each of these are going to require a separate calculation. In step 1, we're heating the ice, or heating the solid. Anytime we're heating, we're using Q equals mc delta T. Okay. Our mass is given in the problem as 1,550 grams. Our specific heat is that of solid H2O, or ice. Okay, so we look at the top of the data table, we see that it's 2.06 joules per gram degree Kelvin or degree Celsius. Remember, Kelvin and Celsius are interchangeable in the thermodynamic world. Then we have our delta T. Well, we see T final is 0 because we're only calculating this section, and we're only going from the negative 70 up to the freezing point. Okay, minus a negative 70, so it is going to be a 70 degree temperature change. Okay. We plug all those numbers in, and we get 223.5 joules. Kilojoules. Okay, so that takes care of the first step. The second step, again, is this plateau, this flat region, which represents the ice melting. So energy is going in, but instead of raising the temperature, it's melting the ice. We still have m, the mass, the amount of stuff, times the latent heat of fusion. Okay? This delta H fusion, we've got to look up at the top of the page. Okay, this data is also on the back of the periodic table. Okay, we see this time it's given in joules per gram. Well, our mass is given in grams, so we do not have to do any mole conversion like we had on, it's joules per gram, that we had on previous homework. So we see these grams cancel, and we are left with joules, and a quick conversion to kilojoules gives us 517.7 kilojoules. Okay. Our Q3, okay, once again, we're going up in temperature, so we're heating. So our Q is equal to MCAT. And our mass continues to be 1550. That will be the same in every step because we're dealing with the same amount of water. Our C is now of liquid water, which is 4.18 or 4.184 joules per gram degree C. And we have a delta T of, it's going to be 25. It's the final minus the 0. So yes, it will be 25 degree temperature change. So we get the Q3 is going to be 162 kilojoules. Okay, so our total Q, our Q total, equals Q1 plus Q2 plus Q3. So we just take these three numbers. This is our Q1, our Q2, and our Q3, and we add those up, and we should get 903 kilojoules. Okay. If we look at significant figures, we've got 2 here, 3 there. It may look like 1 on the homework worksheet. If we have 2, we really have to write it as scientific notation. So we have 9.0 times 10 to the second kilojoules. If you had assumed just 1 significant figure, you could have wrote just 900 kilojoules. But that's how we do that problem. First, we have to determine where on the heating curve we're starting and ending and see which steps we have.